Okay, we are back. I'm a little late today. Day 24. We're starting 10 minutes in. You and the historians at a large grove, AND gates, OR gates, XOR gates, Boolean logic gates. Each gate has two inputs and one output. Ooh, sounds familiar, honestly. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. There are no loops. Sick. Love this. Once a gate has determined its output, the output will not change until the whole system is reset. Each wire is connected to at most one gate output, but it can be connected to many gate inputs. So rather than risk getting shocked while tinkering, you write down all the gate connections and the initial wire values. So this is our puzzle input here. Because gates wait for input, some wires need to start with a value. First section specifies these values. So X00 here. So this is like a machine or a gate, we'll call it. Or wait, no, the whole line is a gate. And this has two values, I guess. Let's read some more. Oh, the wire named X00 starts with the value 1. So there are nodes and connections between them. In this example, simulating these gates eventually causes 0 to appear on wire Z00. Ultimately, the system is trying to produce a number by combining the bits on all wires starting with Z. Z00 is the least significant bit. Oh, so we're going to use BitVec today because I find that easy to work with. And we can specify this however we want. Z1, Z2, and so on. This will allow us to put in like, our bits are 0 or 1, right? Yeah. In this example, there are 3 output bits from the binary number 100, which is equal to the decimal number 4. There's a larger example. After waiting for all values on all wires starting with Z, the wires in the system have the following values. Okay, what decimal number does it output on the wires starting with Z? Let's just create day 24. That's not what I wanted to do. Just create day 24, basically the last day. Let's get a part 1 in here with some test input. Test input wants to read the number 4. Is Z always output? No, there's a bunch of other kinds of output here. I like the idea of petgraph just because we can visualize this, and I like visualizing it for being able to debug it. I don't think we need petgraph specifically for this answer, but I like the idea of being able to see this as a graph and then work our way through it for debugging purposes. So what? This is all of our wires. We've got what? Wires and gates, and they can be connected to anything. So we don't have any duplicates in the first one, but we can definitely do... How do we model this? The second section lists all of the gates and the wires connected to them. So I'm assuming that the wires aren't unique, right? I guess the wires have to be unique, right? So I guess we could treat this as basically like a bunch of registers, right? Basically, the first one is a hash map, and the second one is a set of hash map keys and an output, keys, operation, output, and that's our gate, right? So if we have a gate, then we have our inputs, which will make a vec of string slices. So that means we're going to have a lifetime here. Got an output, which is a string slice, right? So we're keeping the keys, and then operation, which is AND, XOR, or OR. I think we could actually just store these operations, but I'll start with an enum. We're going to have AND, OR, and XOR. These all need to have the same lifetimes, and then I will add a derived debug here and a derived debug up here. So we've got the inputs, the output, and the operation, and then we have a hash map of keys and values. I think these are all bits, right? So they can either be true or false. So we'll store Booleans. So some pretty classic parser stuff for us today. We're going to return a hash map of string slice and bool, as well as a vec of gates, I think. We can always change this to be something else if we want to. Not too worried about it. So then we do separated list line ending. Something that's really probably notable for NOM is that a lot of people think that they have to split on this double new line first and then parse each section. And that's not far off from what you would do, but we can very easily, because we're going to have to parse this first section anyway, just go ahead and parse the first section, then parse the space, then parse the second section. So we don't need to do like a dot split on the middle part because we're intending to parse the entire thing anyway. So we have alphanumeric 0 with a separator of colon space, and then we don't really want bits complete bool because bits operate on individual bits, and we don't actually have a bit. We have a string representation of an int that then gets converted into a bool. So we could probably do complete U8 here. This is separated list 1. This is line ending. This doesn't give us the result that we're looking for yet, but we can separate this out into like input and map, right? And then we use our question mark here, and for the moment we to do, but this will give us string slices and U8s. Now going from bool to U8 is always sound, but casting from U8 to bool is not always sound because obviously you can have more numbers than that. So we will do something a little bit more verbose and include a unreachable here. And of course we have to match on something. So now we're getting a vec of string slices and bools here, and we can kind of let map equals map dot iter, or I guess into iter, right? Because we're going to consume it here. And then we'll just collect it into our hash map, which we don't really need to specify the type of because we will return this. So this will eventually be like input map and then something else. But this will cause us an issue for the moment. So I can just slap that into a empty vec and this would go through. So we can see input here, parse input, we get the gates, we have our error handling, yada, yada. This gives us true, true, false, or true, 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 false, true, false, which is true, 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 false, true, false. That's exactly what we have. So we're good with our hash map. The next segment of our parser, then, if we were going to say like have trouble figuring out what was next, we could debug the input here. And we see that there's 2 new lines and then the start of our next section. So we could start with something like preceded multi-space 1, and then whatever our next parser is going to be. Our next parser is probably a gate, and we'll do separated list 1, line ending gate. And we'll pass the input in here, handle the error, let input gates equals this, bring in these different sequences and whatnot. And then we also need gate to exist. So a single gate here will return a gate, not a hash map or a vec. So in this case, we end up with alphanumeric and XOR or, alphanumeric, arrow, and then thing. So let's copy this up here for a second. So we have a number of options here. Obviously, we could do separated list by space actually here. We could do separated pair to pluck the output and then another set of parsers here. We could do a number of different things. I think I'll do maybe a tuple and just do this all in order. So alphanumeric 1. We used alphanumeric 0 for the other one, didn't we? That should be alphanumeric 1. So alphanumeric 1, operation, which we haven't defined. Operation is like alt, and then tag and, tag or, tag XOR. And each of these can be value. So we can do value here. And I'll just say and for all of them for the moment while I'm typing this out. Or and XOR, which all come from operation. Anybody play that game a long time ago? Thing where you like have the little magnets and the, anyway. random tangent while I'm pulling in these imports. Okay, so we have, this is going to take the input at the end when we're done. We have this set of potential operations. We have alphanumeric operation. Now, we have a couple of options here in terms of handling white space. I think I'm going to write it without white space to start. Alphanumeric, tag. Well, I won't do tag there, actually. I'm going to consider that white space. And then alphanumeric, right? So we've got 3 alphanumerics. We can either choose to put the white space into this tuple parser as well, but I don't really want it to show up. I want it to get dropped. So I'm going to do terminated space for this. I'm going to do preceded space for this. And I'm going to do preceded tag space arrow space for this. And the space 1 is different because it doesn't accept new lines. This gives us a tuple, so we do need to do something with it to turn it into a gate. I'm going to pull it out here. So let input, right, gate, or like elements. Let's call this elements. Handle our error. And then at the end here, we need to do OK, input, gate, fill struct fields. This is always going to be 2 inputs, I believe. So elements.0 and elements.1. Our output is going to be, this is elements.2. Our output is going to be elements.3 and operation is going to be elements.1. And operation doesn't have clone on it, which is why we're still seeing a bunch of issues here. So we'll just add clone. We don't care. It's just an empty enum. So now we have gates here, which is a vec of gate, as we can see, which we can return. So now we have map and gates. And this means gate with inputs, output, operation, inputs, output, operation, inputs, output, operation. I think that's all correct. 000, 111, 222, zeros, ones, twos. Okay. So we are good in terms of the data setup. So we need to run this once, I think is the thing here, right? So the question is, how do we run this? Where do we start? Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. Each wire is connected to at most one gate output, but can be connected to many gate inputs. So there's a question. Do we have, I think these are all just 2 inputs. Really unfortunate that they phrase it like that, because it makes me wonder if a bunch of these are connected to the same stuff. But I guess we'll keep that in mind for later, just in case. My question is, now that we have everything, how do we actually start simulating, right? Where do we start from? Is this a tree? There are no loops, so I guess it has to be. It doesn't specify how we need to start, so maybe we just do them all at once, and that becomes the full set of next values. So let's start with that assumption. So we have this set of state effectively and this set of operations to do. So one step in this process is then, I guess we'll call this mute map. I guess let's not call this mute map then, if we're going to do it that way. We need to do for gate in gates. We do let current map equals map.clone, or maybe not map.clone. I don't know if everything is going to change every time. I feel like we should clone it for the moment. It's also weird that it says like the wires can have, the gates all operate on values that are either true or false. Wires carry 0, 1, or no value at all. So these wires need to be option types, actually, or not inserted at all. I'm going to take that to assume that we need to do a fresh hash map. It feels really strange, though, because there's nothing that produces no value. Why would it say no value? I guess some of these don't get initialized. So 0. So is there a Y 45 or 46 or 47? No, it doesn't look like it. Is there there's no X45 either. I guess the output wires are all the ones that don't have a value to start with. I do feel like I want to visualize this. I'm having a hard time conceptualizing some of this. So we have some with true, some with false, some that aren't here. The ones that aren't here don't have values. We need to effectively find a way to find out which values are filled and then run those operations and then repeatedly do that over and over. So there is a way to kind of do that, but it does use nightly. So we haven't used nightly all month. It could be nice to try to use this. We do need kind of like a second set of gates. So let processed gates equals like an empty vec, and current map. I guess current map is map.clone, right? No. Yeah, map.clone. We don't specify what this is, but this is a vec of gates. And then while, I guess, let gates to process equals gates, and I'm just going to clone this. I'm going to create all new values here. So while gates to process dot is empty, we'll throw the not on there because we're looking for this to be empty. Gates can't be cloned, so we need to go do that. This is fine. Not too worried about it. We don't have that many gates. And I think that we're going to have to keep this state individually anyway. So we have process gates and gates to process. So we do gates to process dot extract if. So to enable a nightly feature, first of all, we have to take this feature, extract if, and put it into our actual, I created an infinite loop. I've done that plenty of times. Let's see, 74597 should be our next text instance. And we should be able to throw this somewhere. So we need to do extract if on a range. This is the whole range. This doesn't exist currently. So not terribly surprised that we see some issues here. Let's break here to start with and see what the compiler has to say. Whole bunch of stuff. Use of unstable library feature extract if recently added. So we're going to go into our bin for part 1 and drop this right at the top. And I'm looking at 1.85 nightly. So I think I should update my nightly. So I'll do rust up, update nightly. So we should be able to run what we just did and do plus nightly. And it'll start building our application once again. And we've got our 2024-1223 compiler We're using extract if, which is the new feature. So we'll just run false here for our return value. And gates to process needs to be mutable for this to work. And I just realized I put this in the binary, which is fine, but we really need it at the crate root. In this case, that's lib.rs for us. So we need to enable it in our library crate. Now, Rust Analyzer is like, hey, we're not using nightly here. So it comes up with a bit of an issue there. So if I do rust up show, it'll show me a bunch of my installed tool chains. In this case, I think we were using 1223. No, we're using 1225, it looks like. No, that's 2022. Wow, that's old. And if we do cargo nightly version, we can see that we are actually on what looks like 1220. So we could specify nightly 2024 1220 here. And I think that should actually go at the root. So I'll move that. And I think we were actually using 1223. Actually, today is the 23rd, so we can't be using 1223. So I'll go back to 1220. And now that we have that Rust toolchain file set up here, Rust Analyzer will pick up on that Rust toolchain file, use nightly for this. It unfortunately is using nightly for everything, but that's a completely separate issue. So if we look at the extract if here, we're extracting if along everything. We are checking. We are actually producing nothing here, but this is going to be where our check for gates to process is going to go. And then we have this iterator that we can then iterate over and do, what are we going to do here? Right, we've got both of the inputs, we've got the output, and we've got the operation. So we'll match on operation here. We do need both of these inputs. So let A equals, we know these are going to be 2 inputs. So gate inputs 0, and this is going to come from current map, right? So this becomes an option bool. We're going to unwrap because this always has to exist. We're going to do this for both of them, right? So we've got A, we've got B, we've got the operation. The operation doesn't want to autocomplete because it's gate.operation. And then we've got and, or, and XOR. So our logic for and is output 1 if both inputs are 1, output 1 if one or both inputs is 1, and output 1 if the inputs are different. I think these line up with the actual logic. So this is like A and B, this is like A or B, and this is A XOR B. And then this break needs to go in here. I think we have an extra curly brace there. This is going to be our value for the output. So let value equals this, and then current map dot, I guess we dot entry. I'm not really sure what we should do here. I'm assuming that gate output is just going to be singular. So this is always going to, in my mind, hit or insert. Current map needs to be mute. So we have false here. So this needs to be inputs.iter.any, or all, I guess, all input key. And this is current map.contains. I guess if it contains the key, it contains anything, right? So it just needs to contain input key. All keys need to be there, which means they have values for us. So these two things we don't use. We can just dot dot there. And I think our final, or one of our final moves. Ooh, interesting. So because we're using current map contains key here, and we're trying to get mutable access to it here, and this iterator then like isn't guaranteed for this to be done by that time, we could solve this very easily by collecting here and then reiterating over the ones that we need to iterate over. I kind of liked the idea of keeping this an iterator the whole way through, but again, we haven't solved the problem yet. So a little bit of allocation is not going to be an issue for us because we don't even know what our final logic is going to be yet, right? So we've got a vec of gates here, and this is cool because then we get to do processed gates, append. This used to be an iterator, so it's called IT, but I guess we don't really need to do that because we're already iterating over them anyway here. So we should be able to do processed gates dot push gate at the end of the day. Processed gates is also not mute. So we'll mute that. And I think that that's all good. That should be a full run. So the question is, we end up with the current map dot iter, right? Dot filter for key value. And the answer here is what? We're going to have a list of outputs that need to be sorted by these integers. So we can just dot sort probably. we'll have to check to make sure that the sorting that we're doing here accounts for 0, 0, or like, yeah, the tens digits. So I'll want to inspect that, I think, on the final. But in this case, it is key and value, and we're going to filter key starts with Z because that's all of our outputs. Then dot sorted by AB, A dot, like A dot 0 dot comp B dot 0 with a shared reference. Sorted by coming from itertools. Did we not bring itertools in yet? No, we did not. The value for us doesn't matter yet. We get that sorted stuff, and then we do what? Collect into a string and print it out for the moment. I think bitvec would be really cool here. I think maybe bitvec later would be really cool here. We should be able to get a string here. So let's do dot map key value to string value as U8 to string. Of course, the sorted by, I believe, gives us a vec. So we have to into iter. Why are we getting an issue on map? Expected a closure that takes a tuple, which is true. And then we end up with casting a reference to a bool to a U8 is not valid, but the value, yes, it is. So then we get like a bit string here, and we can do output equals bit string dot, or rather not dot, I guess, U32 from string radix with the bit string and a radix of 2. Assume this works. Bit string probably needs to be passed in like that, and then we debug output, and hopefully we get a value. Output currently is 1. That's not correct. So let's do some inspection here. So we already know that this is going to be one segment, so let's get that out and do, right, sorted outputs equals this. This is, actually this is an into iter now that I look at the type. So sorted by there, right? So if this is an into iter, then this doesn't matter, like doing that thing we just did to split it out, because this is just going to be that anyway. So current map, iter, filter, sorted by, into iter, map, right? Underscore here, but inspect, debug v, and let's see what we get out of that at the end. We get 0, 1, 2, false, false, true. And I think that we've reversed this is the issue. So we can sort this, I think, in the opposite direction, and we end up with true, false, false, which gives us 4, which is the right answer, I believe. So all good for us. I want to keep that inspect there, but we'll output to string to return that. This test should now pass, and it does not because I didn't add the number in here. It should be 4. At least that was what we were told. Decimal number 4. Here's a larger example. Let's do the larger example. This one is going to be 2024. So we can RS test this if we want to. Probably should have set it up like this in the first place, right? RS test, case, input, output, and then our second case, which is the one that I'm holding in the clipboard right now, 2024. Then we get to pull this and this out and say output, this is case, input, string slice, case, output, string slice. We stick this here and here from our clipboard, and this should now parse int error kind empty. That is really interesting. So case 2 fails, and the question now is why? So can we just work part 1? Oh, no, let's do cargo watch X next test part 1. Maybe we do case 2. I think it's case underscore 2, right? Yeah. Okay. So now we have our thing going on here. First question I have is, did we miss anything in the parser? So TNW, GNJ, let's make sure that we have that in the first place. Again, the kind of thing for advent of code debugging and debugging in general is like start with the beginning and just go through assuming nothing. TNW, PBM, GNJ, that is the last one. So that's all good. So we've got our gates set up correctly. We process all the gates. So that's interesting. All wires starting with Z should produce this string. Does it produce that string is another question. Let's get bit string out here. And bit string is empty. So we're debugging all of these values, right? None of them debug out. So the question is there even anything here? Let's swap this up here for the first things that are going through this. We end up with a whole bunch of stuff and nothing that starts with Z, right? So we do have starting with Z, but why don't we get it? I guess we do what? Gates to process ends up getting empty. So we have to be processing something with an output of Z, right? All of the outputs I'm seeing don't have Z's in them. We should be looping here. So let's do let's see how many times loop comes out here. Maybe we're not looping. Oh, I'm breaking. I intentionally broke there and we aren't doing the full check. Now we pass. I left a break in. Okay. Well, I am okay with that, I think. So let's run this on the actual input. Part 1, parse int error position overflow. So I wonder, we are luckily dumping the bit string out here. How many bits is this? I checked it, there's 46 bits. So we need not a U32, a U64. So we end up with this number, which is hopefully our answer. Yeah, cool. And then we have to do part 2. So what did we do here? Let's get the outputs not logging out. Okay, so we wrote a small parser. The parser is basically separated lists for both of these. This is a gate parser. This is a tuple or separated pair. So we end up with a separated list that has at least one, separated by line endings. This is each line. Separated pairs on those lines with an alphanumeric start, a tag space equals separator, or a colon space separator, sorry. Then a complete U8. So we're parsing a U8. That U8 will be either 1 or 0. If it's not, then it's unreachable. That's because of adventive code. So this turns into not the hash map yet, but the vec of string slices and bools as tuples. So later on, we turn that into a hash map. And then our second parser is preceded by multi-space. So that gets rid of this space in between them. Then we do a separated list of line endings and the gate parser. The gate parser uses a tuple parser. That's a combination of alphanumerics and an operation. Alongside a tag here. We use kind of like preceded to like specify the white space and stuff here. We could write this in a number of different ways. This is just the way I decided to write it. We end up with a tuple here that is 0, 1, 2, 3 elements. And we put those in the right places in the gate struct, and then we use the gate struct. So we have our hash map of registers effectively, or outputs or wires or whatever you want to call them. And we have gates. Then we basically make a couple of variables here. We make the current map, the gates that we still need to process, and the processed gates for this step. I kind of assumed that we were going to have to do this multiple times in part 2. That's why I kind of set it up like this. But you can set this up in a number of different ways, I think. So while gates to process is not empty, then we have to process something. Which ones do we have to process? Well, we can use extract if, which is a nightly feature, to iterate over everything that's there, destructure inputs out, and check to see if those inputs are in the current map that we're working with. If those inputs are there, then this gate can process. We collect that into a vec because otherwise we end up with a shared reference to the map here. And later on, when we try to actually put something in it, because we're doing that in this loop, we're doing an exclusive reference. So those things don't match up. So shortcut, we kind of collect that into a vec. That means this runs to full completion and we don't need the shared reference anymore. So when we iterate over that vec here, then from that map, we get gate 1, we get gate 2. We put those together with some operation. And in this case, we don't try to end modify or anything because we're only expecting that this happens once for each. And we push the gates into the processed gates. Now, we don't need to push them into processed gates, but I was again assuming that we were going to run this multiple times, like in part 2. So we would still need that list of gates. Now, we don't actually need to do this. All we really need to do is clone and then extract if repeatedly. So we probably don't even need process gates. But once we do all of that, then our map, which again is a hash map of the wire to their value, which is a bool, we filter those for the output starting with Z. We sort them in the sort of least significant bit, most significant bit ordering that we need for this to be able to parse. Least significant bit and most significant bit, for those that don't understand what those terms mean, means that is the ones digit on the left or the right of the bit string, right? So if we read this bit string and this is the ones digit, then this is 1, this is worth 2, this is worth 4, this is worth 8. I'm not selecting the individuals, but you get it. As we go out, that number is a power of 2. The other way would be if this was the ones digit and then we went to the right. But we need it in a certain way for this parse to work. So we turn that Boolean into a U8. It's either going to be 0 or 1. We can cast that. This is always safe. We collect that into a string, which I feel like we don't need toString on that, but it doesn't really matter in this case. So we could probably do this conversion in a different way. We get that bit string. That bit string is a set of ones and zeros. In this case, I think there were 46 bits. So we needed a U64, which is 64 bits unsigned integer. And we can do from string radix with a radix of 2. This would normally be a radix of 10 if you were parsing a base 10 like regular decimal number. But if we want to parse ones and zeros, then we parse it like this, and we get that number, which is wonderful. So let's take a look at part 2. After inspecting the monitor device more closely, you determine that the system you're simulating is trying to add 2 binary numbers. X and Y are 2 binary numbers that it is trying to add. So I guess all of the X's and all of the Y's. The output is produced as a binary number on the wires, starting with Z. In all 3 cases, wire 0 is the least significant bit, which I think is the same as the original, so make sure we do that reversal for our sorting. The initial values for the wires are just one instance of a pair of numbers that sum to the wrong value. Ultimately, any 2 binary numbers provided as input should be handled correctly. That is, for any combination of bits on wires starting with X and wires starting with Y, the sum of the 2 numbers those bits represent should be produced as a binary number on the wires starting with Z. For example, if you have an addition system with 4 X wires, 4 Y wires, and 5 Z wires, you should be able to supply any 4-bit number on the X wires, any 4-bit number on the Y wires, and eventually find the sum of those 2 numbers as a 5-bit number on the Z wires. One of the many ways you could provide numbers to such a system would be to pass 11 on the X wires, 1011, and 13 on the Y, 1101. If the system were working correctly, then after all gates are finished processing, you should find 24 on the Z wires as the 5-bit number. Unfortunately, ours is bigger. There are exactly 4 pairs of gates, whose output wires have been swapped. A gate can only be in at most one such pair. No gate's output was swapped multiple times. So, for example, the system is supposed to find the bitwise AND of the 6-bit number on X through 5 and the 6-bit number through 5, and then write the result as a 6-bit number on 0 through 5. However, in this example, 2 pairs of gates have had their output wires swapped, causing the system to produce the wrong answer. The first pair of gates with swapped outputs is 5 and 0, which is made somewhat obvious by the numbering, but I assume that's not going to happen in the real input. Second pair of gates is 2 and 1. Correcting these 2 swaps results in this system that works as intended for any set of initial values on the wire for X or Y. In this example, 2 pairs of gates have outputs that are involved in a swap. The gates that need their outputs swapped could be anywhere. If you were to determine that you need to swap output wires A with E, O with Z9, and B with K, and AOC with Z24, your answer would be AA, AOC, B, C. Okay, so lexical ordering of the swapped gates. Your system of gates and wires has 4 pairs of gates which need their output wires swapped, 8 wires in total. Determine which 4 pairs need their outputs swapped so that your system correctly performs addition. What do you get if you sort the names of the 8 wires involved in a swap, then join those names with commas? So, feels like a search space in some sense. We have how many gates? A lot. Let's take a look at the input here. So if we were super naive about this, we have about 222 outputs. We would need all of the 2 tuples of combinations for them. We would then need to do like the combinations or something like that. I think the order matters. So, well, the order doesn't matter. So yeah, I think combinations of all of those groups of 2. So if we have 222 outputs, those outputs are paired off as combinations, and then we need the 4 combinations of all of those. We could run that all the way through, grab all of the inputs for both of the values, and then just brute force it and see which combination of outputs produces the right result. So this is like 1.5 trillion possibilities for brute force. We get like, what was the number? It was like 2512 or something, right? For like 222 and 2, right? Picking two options out of a set of 222 gives us about 2512. I don't think that's the right number, but it's like 2500-ish. And then taking 4 from that and getting the combinations, that gives us like a trillion or like a 1.5 trillion options effectively, like 1.5 times 10 to the 12th. So quite a bit. A trillion microseconds is like 11 days. So that would take a while. So we need another option. Let's get all this input back in here. So I think that one of the things that I want to do here is possibly visualize this. We do have the bit string from all the outputs and stuff. So we should be able to actually let's start with this, right? We should be able to actually read these numbers in as bit strings themselves, right? So we've got, what is it? This random thing for bit strings. Let's do no processing, literally no processing, right? Because we're going to do map bit string X, right? And this should get us the X number, right? I think it's X and Y, right? So this will be what we start with. We have X, and then we want radix should not change to ratty. So we bit string Y, and this should give us cannot volume value current map. Where's current map? Current map has got to be down here. So these bit strings gone too, this gone, and then we just to do, this is just going to fail. It's going to be fine. We end up with these two numbers. And let's also debug the outputs. So let's do bit string X and output X, and bit string Y and output Y. And it said that we're trying to do addition, right? So output Y plus output X. And we want to print line this number with bytes. And we end up with this number and this number. And we end up with this number. Actually, let's do this output Y plus output X format byte string this. And then we end up with the same thing 3 times. So if we take a look at this, then we should end up with, we'll say X, say Y, we'll say addition. So we end up with basically a prefix here that we need to have. The question in my mind is, do we need the output? I think we do need the output actually. Like we need to run this. So let's let this run. And then we end up with some white space issues. And not output to string, but debug what? Output. And output is this. So this is the number that we are actually getting. And this then is something we should be formatting into bits, right? So we yoink this back down here. This is going to be output in both places. Run this, it does it. This is our output. So we end up with whatever this is being our first one. Then we immediately have another. Then we have this one. And then these two, those 3, that one. Yeah, and then it gets futzy, real futzy down here. So each side is pretty good, right? Say it's good until here, and this is good until here. So this, if we think about it, is Z0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So Z11 has to get swapped with something. And I don't know what the makeup of this actually is. So I do kind of want to jump all these into PetGraph and do a .viz on it. If we look at the input, all of the outputs have potentially other issues. So Z11, right, could be an issue with QKC or QQW and so on and so forth. So let's jump all this as nodes into everything. So I think we ignore all the operations, and all we have to do is drop all these node names in and use the inputs and the outputs. So we did this yesterday, right? Did we do this yesterday? We did this recently. I'm starting to lose track of when we do things. So we need that, and we need this. We don't care about the values at the moment, I don't think. We might find a way to pull them in. So this would say from edges, right? And really from edges would be gates.iter.map, gate, fill struct fields. So we've got inputs and outputs. Technically, we also have operation, but we're not going to use it. So I'm going to dot dot here. We are going to use inputs and outputs because we need to generate like vec input 0, output, input 1, output, which we could do more generically like this: inputs.iter.map, input, input, output, collect. So we want to flat map this actually because we're creating that nested structure like we usually do. We're going to let edges equals this. We are going to, I guess, we don't need that collect here, but let's make sure that we are generating something that works. For now, we have impl iterator, so we will collect on the outer, which gives us a vec of double reference to string slices in both places. And this claims to be a string slice, but if we change that type, then it's correct. And then we can dot viz this to see what it do. Part 2, run. I did that in part 1. Luckily, this is entirely ugh. I've done this multiple times. I don't know why. So let's do that here so that when we run part 2, it actually shows up. I mean, I guess seeing it on part 1 would be cool too, but that's not what we're doing at the moment. So we have .viz. We are .viz enabled at this point. All of the edges are unlabeled, or rather unit at the moment. We're gonna do graph dot dot, and I want to drop this into the day. So we're up 1 level, and then toggle preview, and we end up seeing something. This is a whole bunch of stuff. So actually we could just do this by hand, I think, or rather work our way backwards, right? Just kind of mark things off as they're correct or incorrect. And then we will find the ones that need to be changed, and they will very likely be related in some way. I also realized that I made this like undirected when in fact it is very directed. So we should make this a digraph map because it is actually a directed graph map. Funny how that works, right? So we're going to get this directed graph map out of this. What do we do about save, toggle preview? Oh, that's super interesting, actually. This is like a totally different graph and layout. We could just work our way backwards. Here's 45. I think 45 is correct. So we just work our way upwards through this tree. Wow, this looks so much easier to work our way through now that I've laid it out in a directed manner. This is very clearly like a tree, right? Interestingly, like 7 is used as an input for 2 different ones. So we will have to kind of like work our way through this in some sense. Are we going to bring out Photoshop? So if we go into day 24 and I generate this graph and we pull that into a fancy program called Photoshop, then this is what we'd end up with. And oh, look at that. If we use Photoshop, we can invert it. I think that for these edge weights, I want to use the values that are processed by the program. So for part 2, maybe we don't do this up here. Here's our edges currently, but really, yeah. Gates.iter, gates, inputs, outputs. We're iterating over the input, doing input, output. And this is from edges, right? So digraph map from edges, node ID, right? From edges. Edge weights may either be specified in the list or are filled with default values. How do you specify them in the list then? Iterable I, into weighted edge, node ID n. So if we say that this is going to be an edge weight of U8s, that initializes us. So I think that for all of these, I think we want the inputs as the edge weights because we're going input to output, and then the output then would keep going. So we want current map.get input.unwrap. And this is bools, actually, now that I'm thinking about it. So like this would be bool, actually. And we are left with this is reference to bool, not actually bool. So hopefully we get, yeah, the values here like this. So let's pull this. This will be our digraph. Then we have all the values as they are being generated, and we can mark them all one by one as a success or failure. And I feel like this will be actually, once we do this manually, we won't actually have to do it in any other way. But, you know, it is what it is. Let's make this way smaller. Let's make this red, I guess. Oh, I don't want that. I want a new layer, and I want red and green as very bright values. So we'll have red and we'll have green. So I'm just going to start marking these off. And I think the good part here, let's get editor, editor and Photoshop on the same side here. That's not editor. Move this back. Okay, now we've got editor. And now we've got these, right? This is our actual output. This is the output we're looking for. We know that, what? I guess this is Z45, right? Starts at 0. There's 46. So this is Z45. So we think that 45, 44, 43, 42, 41, 40, 39. So I'm going to mark this as green. 44 is green. 43 is green. 42 is green. 41 is green. 39 is green. 40 is green. Question is, did I get them all? 45, 44, 43, 42, 41, 40, 39. So all of those are correct. And then 38 is incorrect, right? There's 37. Where's 38? 36, 39, 38, 38. I can't find it. Let's look in the file. Z38 is index 232. 232 is 145. 145 is SQJ. So we're looking for SQJ and 38, which for some reason I can't find in the place that I would have expected it. Is that because it's way up here and it's one of the ones that we actually have to directly swap? That's super interesting if so. This is a lot of nodes. Okay, the other thing is that what? We need to, is any other information here useful, right? Like we do have all of the operations that need to happen and or an XOR, and that's in the input. So like NRV or JSP, right? So technically speaking, one of those could be false. And we're assuming that the X and Y numbers are fine, right? So like this, that's not what I wanted to do. This is fine, right? These are all okay. So if we assume that these are true, then JSP is and. So and, absolutely correct, right? I know that these are going to be correct down here. I'm just going through a little bit of the process. This is XOR. Output's true if the inputs are different. So XOR would have to output false, and it does. So that's correct. So I think we just work our way basically down like this. We'll find all the branches that end up being wrong. Those outputs are the ones that need to be swapped. And then we'll have all the ones that need to be swapped. We don't actually need the order that they are swapped in. We just need to know which outputs to swap, right? Just make sure that before I go through this whole rabbit hole, that gates need their outputs swapped. So the output nodes would be what gets swapped, and their edge out is what gets swapped. Or their edge out changes because of them getting swapped. So technically it could be anything. So we do actually have to check the ones, even the ones that look like they are fine, I think. So JSG and HKS, this is good. HKS, TNC, or DBJ, neither, so false, so that's correct. And I'm just going to do this up the tree. I'll probably talk a little bit more when we get to one that fails. Okay, well, it's getting pretty late here. I'm going to play with some more visualizations. I think that visualizing this is the way to go. I've spent quite a bit of time on this because I don't know what this structure is, and reverse engineering a structure that you've never seen before is really tough. So I think this might actually be an opportunity for me to learn a little bit about what this structure is. I think that doing a visualization here, making the graph show these XORs will show us what to swap, because I think the front of this whole chain is going to show us a pattern here as soon as I can visualize it properly. And that these are all going to be like, this goes into an and this is an XOR, and then this is an OR, right? And if we figure out that pattern, for example, let's say XY splits into like and XOR, and goes to OR, right? And an XOR, and that and goes to an OR, and that node goes to and an XOR. And then the XOR goes to another and an XOR. And the and for here goes to an OR, which then itself goes to an and an XOR. So like there's a pattern here. And if we go check, I don't know, let's start with 11. So 11 goes and an XOR, right? Which follows the pattern for both of them. the AND branch should go to an OR, which it does, and then to an AND and an XOR, which it does. And the XOR branch goes to this, which should do an AND and an XOR, and it does. The AND here goes to a thing that then goes to OR and then goes to AND and OR, which looks correct. So if we look at 10, which is the one preceding it, which I think might generate the value that goes into 11, which is the wrong one. These have AND and XORs. So the AND goes directly into an OR, goes into an AND XOR, and the XOR goes into an AND and an XOR, and the AND on the XOR goes into further, and the XOR goes into the Z. But in the next one, the AND goes into the Z, and the XOR goes into the future. And on 9, I think that's one of the issues there. So there's these patterns here that we can look at where we can identify the faulty wires. And as long as we identify the right faulty wires, then we can put all of those together and get the answer. I unfortunately don't have an explanation for whatever structure this actually is, but I'm going to go try to visualize this a little better so that I can more efficiently find these wires. And I'll see you tomorrow for day 25. Okay, so I did get this before I actually ended up going to bed. So I figured I would hop back on as editor Chris and explain kind of what I did, because this is very much further down the path that we were going. So I basically have a ton of dot graphs. I went up to like 6 dot graphs at this point, and I've been manually changing my input as I find nodes that look like they're correct. So if we take a look at one of these, which is going to be a big white flash screen, then I think at this point I was looking at X11 and X10 for what the issue was. So if we go back to my work log here, earlier in the video, we spit out all of the bits for X, all the bits for Y, and all the bits for the addition. This is the actual output that we got the first time we ran the program, which ends up with this bit sequence. So comparing the value that we got from the program to the value that we think it should be, this addition, which is just a manual addition, like add these two numbers, show it as bits, then we end up with like a bunch of sequences at this side that are correct, followed by 2 positions that aren't, a bunch of positions that are correct, and then a bunch of positions that aren't, and so on and so forth. So what I ended up doing is the right-hand side here is the top of the graph we were looking at, right? So this graph, when we think about the X0, X1s, X2s, those are the right-hand side of these bits. All of the Z, this is Z0, this is Z1, and so on and so forth. So we know that these like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like the 12th bit or something like that is the one that's wrong, right? So somewhere around there, there's a node that's an issue. Now, to figure out exactly what node was an issue, see if I can find I have multiple attempts at doing this. So here's one of the older ones. But we end up with this like set of patterns, right? So we can start with an X and a Y node. And then we have an AND and an OR, XOR, that both take inputs from those X and Ys. And then that gives rise to a set of rules, basically. So if you are at X and Y and you see the XOR branch, then you follow that to the next XOR. That is usually the Z output most of the time. It's supposed to be the Z output. If you follow the AND branch, it should hit an OR node and then split again into AND and XOR, where the XOR is the Z output. To show this a little bit more concretely, we can go to one of the ones that actually works, which I think 9 works here. So we've got X here on the left and Y here on the right. Then we've got a split into XOR and AND. AND will go into OR, and if you follow that OR to XOR, that is a Z position. And this is basically always true. So if you take the other end, the XOR and the XOR, that gives you another Z position. So you can follow these 2 trails to find the places at which you should get a Z output. So this is graph 3, which means I think that Z11WPD was the issue. Yeah, Z11WPD. So look at this. Like this Z11 here is an AND, which is the wrong value, because if we go through the XOR and we go to the second XOR, this should be the output right here. So because this is not the output, we know that this has to reconnect to the output. Well, no is a little bit of an overstatement. We can make an educated guess that this should be connected to the output. And then it just so happens that if we look at the rest of the pattern, you end up with this like and then this one would be an or, so on and so forth. So these two look really good, like candidates that could swap. It doesn't mean they will, it doesn't mean they are the right ones, but they are pretty good candidates for a swap. So from that step, it's basically swap them in the input. So go back to, my actual input here, and I literally just changed these lines. I took the output and just swapped the two outputs for the two lines and ran it again. And when I ran it again, I got graph 4. And graph 4 has the new output. Each run, see if I can run this. We've seen this run before in the video, but every time we run, I'm putting out this output like we did at the beginning and printing the bit pattern. We take the new bit pattern, and I'm sitting over here comparing it to the expected bit pattern each time. So here we get to here before we have to find an issue with, like Z11-ish. Here we get all the way down to here. And as we go down this list, I'm basically swapping out nodes. And when they succeed, it gets further and further along this bit list towards the end of the graph. And at the end of the day, we find one that works out. Now, I think this format, or like this input, is specially formulated to make this an approachable approach. This definitely doesn't feel like it would work in the general case or anything like that. So yeah, I think that's it for today. Basically just start at the right-hand side, start at the top of that graph, use a GraphViz output, know the pattern, which I think I didn't commit this. Okay, let me pattern.md, we'll call this. So this will be also committed. And basically like find these two patterns, try to track them through the graph. When you have an issue with a node, then try to figure out which nodes swap to make this pattern correct again. Now, this isn't always true, but it mostly held. And I think there was one issue where, Z19, if I remember correctly. Z19 is a terminal node, like it stops there. It's like XX and then goes in. So let's look at the input here. So like we've got X and Y here, and it just ends immediately in Z19. But this is an AND, so we know it has to be an XOR. So there has to be something close by for it to swap with. And there is an AND close by that is also in the wrong position. So it didn't exactly fit, I feel like, but it was close enough and it worked out. So that's it for today. I know this isn't a super satisfying explanation. There is an actual structure. It is actually called like a ripple adder error or ripple carry adder. I never learned about ripple carry adders, so unfortunately I didn't get to really lean on any of that information, but that seems to be what the actual answer was. It's a ripple carry adder, and thus you should be doing something with the rule sets that arise from that. I unfortunately have no idea, or had no idea up until tonight, what that was, so I couldn't rely on it, which meant it took quite a while. But it's day 24. If you're still sticking with it, congrats. One more day, and I will see you in the next one. Have a great rest of your day.